So the paper is called Agricultural Robotics, a State-of-the-Art Survey, and Luiz Oliveira, the platform is yours.
Hello everyone, can you hear me?
Yes, and we can see the presentation.
Okay, I will present our paper, Agricultural Robotics, a State-of-the-Art Survey. Well, there are currently about 7.6 billion people on the planet, and by 2050, this number is expected to increase to 9.8 billion people. The growth in the world population brings with it several types of issues, such as the need to increase the food production in increasingly smaller agricultural environments, since around 68% of the world population will live in urban environments by 2050 and will need twice the current food production capacity. The percentage of arable land has significantly decreased, since in 1991 it represented around 39.47% of the land area, and in 2013 it reduced to 37.7%. With the proposal to improve people's living conditions, the increase in the global urbanization process tends to increase individuals' financial income, which makes people seek a healthier way of life and nutrition. Finally, rural producers are automating agricultural activities to maximize their profits, and also due to the lack of qualified employees to work on farms. Robotics applications in agriculture. Tasks such as harvesting, pruning, and spraying cultivation areas are chosen to be improved precisely because such activities are performed manually, involving labor costs and over-application of expensive chemicals. On the other hand, the task of estimating food production allows the agricultural producer to have greater control over their production, identifying possible situations such as disease on the plantation that are impossible to be detected by naked eye. Robot for land preparation before planting. Among various functions, the Caesar robot, this robot, can perform the task of fertilizing the soil, both remotely controlled by a human and autonomously. To navigate the plantation, it uses the real-time kinematic technology for the GNSS, capable of improving location and positioning accuracy to about 3 centimeters. With a 4-wheel steering system, 4SS, to maximize its maneuverability, the Greenbot robot, this robot, was the first commercial robot completely used to perform repetitive tasks, such as sowing, plowing, or fertilizing 10 hours a day, transporting up to 750 kilograms and 1,500 kilograms in front and rear compartments, respectively. It has a bump sensor to detect obstacles ahead and make emergency stops. Robot for sowing and planting. The Lumai 5 here was developed to perform wheat sowing with high precision. To improve its maneuverability, it has a 4SS system. The challenge for this task is to carry out the sowing maintaining the same distribution for different speed of locomotion. The experiment results showed that the qualified rates here of seeding exceeded 93% in different sowing speeds. Robots for plant treatment. To take advantage to the constant exposure to the sun while carrying out weeding activities, the Reaper and Ladybird robots were designed to contain photovoltaic panel in their mechanical structure and thus recharge their battery systems. A stereo camera creates RGB images of the crops, and a hyperspectral imaging camera captures IR and UV data. The spectral information allows the system to identify the shape and the color of the crops, and their spectral fingerprints provide data on their health through the use of a number of previously trained machine learning algorithms. A controlled quantity of herbicide is then applied in exactly the correct position. Equally, if the software identifies a plant in a poor health from its spectral characteristics, the robotic arm can deliver an appropriate quantity of fertilizer to it. Harvesting. Committed to the strawberry harvesting, researchers developed the location of fruits and perception of the environment by means of a robot equipped with an RGB depth camera. The researchers focused on the development of three tasks: the detection of strawberries through deep learning networks, RCNN, a trajectory planning algorithms to plan the collision-free action of picking strawberries based on 2D images and the 3D point cloud, and tests performed in a real environment. After carrying out several experiments among all RIP strawberries identified, 74.1% were successfully harvested. And the old estimation, the Agrob V14 robot was designed to work autonomously even in the event of GNSS signal unavailability. It proposed a new approach to the simultaneous localization and mapping technique, SLAM technique, by inserting radio frequency identification tags, RFID tags, located at the beginning and the end of each row of the vineyard to allow the reduction of the complexity of the 2D extended common filter used. The authors conclude that the Agrob V14 robot can overcome ditches, rocks, and high slopes up to 30%, although these characteristics impose difficulties to the robot, which reduce the detection of natural characteristics by the laser rangefinder. Discussion of existing applications. The applications previously described and the many others are shown in this table. It's possible to observe that most robots present a 4WD system, four-wheel drive system. This is due to its ease of construction, control, and the vast majority of the plantation soils that are not rough and steep. It's noted that, unlike the landing, preparation, and sowing robots, all robots associated with the treatment of the plantation have some computer vision algorithms showing the different levels of difficulty between each agricultural activity. Due to the difficulty of developing an accurate and reliable systems that replaces manual labor, most of the reviewed studies sought to build robots with a low-cost computer vision system that is using conventional RGB cameras, like here, 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 and so on. Unsolved issues. As noted in Table 1, most of the employed robots use a 4WD system. However, robotic systems with wheels are strongly affected by terrains containing stone elements or cavities, because for their locomotion, the wheels need to be in constant contact with the soil. For this reason, the constant locomotion of such robots throughout the plantation results in a high rate of soil deterioration. In this sense, the improvement of the energy consumption of the UAV, an unmanned aerial vehicle, and therefore its flight time, enabled its greater efficiency in carrying out agricultural tasks without contact with the soil. Another research possibility is the use of robots with other forms of locomotion, namely legged robots, as they are able to move in irregular and unstable terrain. In addition, they do not need the constant contact with the ground for movement, and the damage caused to the plantation soil is much less than that of wheeled robots. Since only Caesar and Greenbot robots are commercially available, another proposal ought to be development of a new research based on legged robots already available for use, that is, off-the-shelf. As examples of off-the-shelf robots, two stand out: Animal, here, red robot, and Spot, here. Both these robots are quadrupedal, and have their own solutions for navigation systems, trajectory planning, computer vision, and have an intuitive programming interface for the development of new applications by researchers. Regarding to the development of robots with navigation systems based on GNSS signals in agricultural plantations whose height of vegetation or the conditions of the local environment impair the reception of GNSS signals, the improvement of SLAM techniques may contribute to a more efficient automated locomotion. Finally, as we are going through the process of the fourth industrial revolution, applications in cyber-physical systems have been in great demand by large companies in the sector. In this sense, the integration between the various applications of agricultural robots and the Internet of Things, IoT devices and sensors can together maximize the control and the monitoring of crops, sharing machine-to-machine information and displaying them in a simple form to the rural producer. Final, through a discussion of why such systems or techniques are more appropriate to perform certain tasks, for precision agriculture closer to real field conditions, improvements in locomotion, navigation, and vision systems are required. Navigation and vision systems in rough terrains are required, in addition to greater integration between the various robotic systems and IoT technologies. Therefore, the present study sought to contribute to the state-of-the-art of agricultural robot applications, transforming large farms into smart farmings. Thank you for watching.
Thank you very much, Mr. Oliveira. Is there any question from the audience? I would like to ask something regarding the results of the study, because you mentioned that one aspect, for example, is that the animal-like robots, like the quadrupedal robots that you saw, the leg robots, for example, can be a possible direction for the future, and at the same time also the UAVs. But where do you think we are closer to see the next step in this development of agricultural robots? We will see more drones flying around the crop sites or more leg robots? What is more feasible according to the results of your study?
I think is the UAV, because for the legged robots, there are many legged robots, but in prototype stages, and the there are many UAV in commercial stages, and I think for the briefly future, there are many UAVs applications.
All right, that would be nice. That would be nice to see. Is there any other question, comment? No. So I guess with this presentation, and thank you very much, Mr. Oliveira, I think we conclude the session.